Okay, I'd like to give you a couple pointers on handling elliptical orbits. An elliptical orbit, is the more general case. In fact, all closed orbits are actually ellipses, and you can just think of a circular orbit as the special case where the ellipse turns into a circle. For an elliptical orbit, and we're assuming I'm going to limit myself to the case where the mass of one body, which we're going to call the primary, is much bigger than the mass of the smaller body. So the big one, essentially, stays in place, and the little one orbits it. So if the little one is orbiting in an elliptical orbit, you'll have two foci of the ellipse, right? And from geometry, you should remember how the focus of an ellipse, or the two foci of an ellipse, are, how they have to do with the shape of the ellipse. Okay, I won't go into that. But at one focus, you will have the primary body, and at the other focus, you'll just have empty space. Okay. Um, what this means now is that the speed of this guy is going to vary as it goes around the ellipse, because sometimes it's coming towards the primary, sometimes, like down here, it'll be going away, and sometimes it'll be speeding up, sometimes slowing down, etc. So what we're going to use here to do this analysis is we're going to use first mechanical energy will be constant, okay? And a mechanical energy is kinetic energy plus potential. The only potential energy here is gravity. Okay, so what you're going to have is 1/2. Actually, let me write it over here. 1/2 the mass of the little body, its speed squared, minus, and then you have the big G, big M, little m over whatever this r distance here is. Okay, so this is your mechanical energy. This will be constant. Okay, and this is conserved. So the second thing is we need another conserved quantity if we want to be able to solve for anything. So what we have to do is go back to our rotation unit and look at how the gravitational force acts on this little m guy. So at any given point, the little m guy is subject to a gravitational force from the big one, and that force always points straight towards the big one. What this means, so right there, and right here, it'll be like that. What this means, because this force always points straight toward the center, so basically the gravitational force, come on, is always parallel, let me just write parallel to the r vector, or actually, I should properly say it's anti-parallel. So it's parallel to the negative r vector, which means it points along the line. Well, the line of action of the force is the same line as the r vector is in, and that means the torque due to gravity, okay, about the sun is going to be, about the primary body. In this case, I'm going to say it's the sun. It's going to be 0. So this force is never going to exert a torque about the center or about the primary body, because it's always pointing towards the primary body. What that means then is that angular momentum of the little guy about the big guy, so I'll say about m, okay, is also conserved. Okay, so now what does, it looks like ACO, so now it just looks horrible. Okay, so how do we define angular momentum? Angular momentum is a vector properly. Okay, so we go back to our angular momentum of a particle about some point, and we say the angular momentum about point m, the angular momentum of the little mass m, mass little m, about this big mass is going to be equal to this r vector, okay, whatever it happens to be at the time, whether it's this r vector here or this one, okay, crossed with the mass times, or the mass of the little guy times his current velocity, or this little term here is his linear momentum, okay? So what that means now, let's recall how we can evaluate a cross product, okay? If we want to just find the magnitude of it, then what we say is the magnitude is going to be equal to the r vector times m times v times the sine of whatever the angle between them is. So let's define what our angle between them is. Here is your r vector, okay? And I'm going to extend this on a little bit, okay? Because we're going to say right here is your guy, okay, with a mass of m. And let's say his velocity at this moment is like that. Okay, the theta, or this angle theta here, is this angle here, because this is the angle between the direction of the r vector, which is this way, and the direction of the v vector, which is that way. So that angle there, the sine of that angle there. Now, this is not easy to deal with when you've got this curving path and he's always changing directions and the r vector is changing and it's not pointing always, in a nice direction. Velocity is not pointing in a nice direction. This can get ugly very quickly. So we really only do this at two particular points, okay? So at this point, at what point do we want to do number 2, I guess is what I'm saying. We only find L at, so what kind of points do we want to deal with? Well, we want to deal with points where basically sine theta works out to be nice, okay? So there are 2 nice possible values for sine theta. Same goes for cosine, but for sine theta, the 2 nice values are 0 and 1, okay? So let's look at 0 first. For sine theta to be 0, we need this angle theta to be 0, which means we need the velocity to be pointing in the same direction as the r vector. And if you think about this, as this sweeps around, you can pick any point here, draw the r vector, draw the velocity, which has to be tangent to the orbit, and you'll realize they're never going to be parallel. They're never going to go in the same direction. So sine theta equals 0, huh? Well, no. Okay, so what about sine theta equals, what's the other nice value we can have? 1. So where does sine theta equal 1? Sine theta equals 1 when theta equals 90 degrees, okay? So theta equals 90 degrees, and when theta is 90 degrees, kind of obviously, velocity and this r vector are going to be perpendicular, okay? Not hard to figure out. There are 2 points where that happens, and they are this one here, okay? So this point here and this point here. Makes sense, I hope. So these are the closest points and furthest points from the primary body, okay? So we only find L at 2 points, I guess I'll say here, okay? And those 2 points are the closest approach, okay, which are, closest approach, which can be called, in general, it's called periapsis, okay? Periapsis, okay? Peri is Greek or Latin, whichever, meaning close, and apsis just, I don't know, is Greek or Latin for apse, maybe, I don't know, I'm not sure. But periapsis is the closest approach, okay? If it's the sun, it's called perihelion, if the primary body is the sun, okay? And if the primary body is the Earth, it's called perigee, okay? But periapsis is the general term for any orbit. So periapsis is always correct. Perihelion and perigee are only correct if it's sun and Earth, okay? And so this is one point we do, closest approach, and furthest. I wouldn't call it furthest approach because it's not approaching, I don't know, furthest away, whatever. You fill in the blank. Furthest something. Find a vocabulary word for that, okay? That's your assignment. So, and the prefix for that is apo. So apo means furthest, I guess, where peri means closest. So these, of course, fit. You can use the same, suffixes. So apoapsis is the general one for any orbit. Furthest from the sun is called aphelion, and furthest from the Earth is called apogee. Okay, but again, the really important things to remember are apo and peri. Okay, and if you remember these, then what you can do is say at this point when you're at closest approach, let's say right here. Okay, so this distance here is r. We can call this r sub p for periapsis. Okay. And then we can say the velocity is v sub p for velocity at periapsis. And then you can say angular momentum is radius, or it's not radius. It's not a radius, but r value at periapsis times mass times speed at periapsis. Okay? And that is for periapsis. Okay? At apoapsis, now you're out here, r is this way, v is this way. They're perpendicular. Remember, that's the whole point. Sine theta is 1. So RA times M times VA. Okay? And use the fact then that L is conserved. Okay? If you get a problem about an ellipse and you're dealing with something at apoapsis and periapsis, or apogee, perigee, whatever, use this fact. Use the fact that you can calculate angular momentum at those 2 points, and that it will be the same. And you can use the equality of that as one equation, and then the fact that mechanical energy is conserved as the other equation. So you can see also for EMEC, you can plug in like VA and RA, and then also VP and RP for mechanical energy at apoapsis and at periapsis, and then you could have another equality. And this doesn't necessarily look pretty, but it will work, and you can use it to find things. So the next video, I'm going to try to do a sample problem about Halley's Comet and show you how you might make use of this. Okay,